Let's try a video key for the assignment I gave you today on drawing Lewis structures and drawing them correctly, looking for formal charges. So remember, with the first structure, count all the valence electrons that are available. So we know nitrogen's bringing 5, and we have 3 times 7 from each bromine. And so that's going to give us a total of 26 electrons to put into bonds and to satisfy octets. So we'll place our central atom, and we'll put the bonding atoms in an arrangement that we think it's going to be correct. Start counting our electrons. The first electrons go towards the bonds, and that's 6 of them. Then we have 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 2 left, and remember, they go on the central atom. Now we'll check the formal charges to see if this is the most reasonable structure. So remember, there's 2 ways you can do it. You can follow the formula, which is the number of valence electrons the element has, minus the unshared electron pair, minus the shared ones in the bonds, divided by 2. So let's look at the nitrogen first. So nitrogen has 5 valence electrons. In this structure, it has 2 electrons that are unshared. In this structure, it's got 3 pairs of electrons that are shared there in the bonding. So that would give us 6 divided by 2. So we end up with 5 minus 2, which is 3, divided by, or minus 6 divided by 2, which is 3. So that gives us a formal charge of 0 on that nitrogen. That's a good sign. Let's check the bromine. We only need to check 1 because they're all the same. So we'll do the same thing. Each bromine has 7 valence electrons. On this diagram, they have 6 that are unshared. And they have 1 shared pair, which means you have 2 electrons divided by 2. So we have 7 minus 6 minus 1, which gives us 0. And so each one of those has a 0 formal charge. So this is the most favorable configuration for this molecule. If you don't want to use the formula way, you can use the how many valence electrons does it have normally versus how many does it have in the structure. But remember, with that, you've got to imagine those as 2 electrons and not just that 1 line, because we want to see what everybody's bringing into the bond. So the same thing as with the nitrogen. Nitrogen should have 5, and let's see how many it does have. It has 1, 2, 3, 4, 5. So 5 minus 5 gives it that formal charge of 0. And each bromine should have 7. And let's see what they have. They have 1, 2, 3, 4, 5, 6, 7. 7 minus 7 gives us that formal charge of 0. So either way you do it, you'll come up with the same charges. Okay, let's look at the structure of a polyatomic ion. And so again, we're going to add up our electrons. Nitrogen's going to bring 5. We have 2 oxygens, each bringing 6. And then we have this extra electron due to the charge, and so that's an extra 1. So that's going to give us a total of 18 electrons. So again, we're going to place the atoms the way that we think they're going to form bonds. And now we're going to put our bonding pair in first, and then satisfy the octets. So we've used 4, 6, 8, 10, 12, 14, 16, and the extra pair are going to go back to the central atom. So looking at the structure, you see that nitrogen's octet isn't satisfied. So remember, if you have too few electrons to satisfy octets, we're going to suspect multiple bonds. So let's take these 2 away from the oxygen. Or not away from it, we're just going to move them into the bond. So remember, everybody gets credit for those electrons. So if we check the octets of each of these, we see everybody's satisfied. Now let's check to see if this is a reasonable structure by looking at the formal charges. So let's look at the nitrogen first. So we can do it both ways. We can say nitrogen has its 5 valence electrons. We can see here it's got 2 unshared pair. it's got 6 in a bond divided by 2, which gives us 3. So 5 minus 2 minus 3 gives us a 0 formal charge on that nitrogen, and that's a good sign. Let's do the same thing for the oxygen on the right. We've got 6 valence electrons. We've got 4 that are unshared. We've got 4 that are in the bond divided by 2. So 6 minus 4 minus 4 divided by 2 gives us a 0 charge on that oxygen. So far so good. Let's try the formal charges on this oxygen. 6 valence electrons minus 6 unshared electron pair. And we've got 2 divided by 2, which gives us a 1. So 6 minus 6 is 0, and here's our negative 1. That's where that charge comes from. So this is as low as you can go. We have a 0 formal charge on the central atom, which is good. So this is the most reasonable structure. So we'll commit to this one. But before we do, we've got to, let's leave our charges on there. We need to put the whole thing in brackets and put the charge on the outside. So resonance, since we have a multiple bond there, we're going to have that resonance structure. So the first structure is as we drew it. The second structure would have the double bond on the opposite side. And if you put in your unshared pair again, and then add your charge to the outside. Okay, we'll look at the last structure, sulfur dioxide. So add up your valence electrons, 6 from the sulfur plus 2 times 6 from the oxygen, so that gives us a total of 18 electrons. Find your central atom. Put your bonding pair, or your bonding atoms the way you think they're going to go. Use the first electrons to make the bonds. So far we've used 4. Add the rest to satisfy octets. So 4, 6, 8, 10, 12, 14, 16, and the remaining 2 are going to go onto the central atom. So looking at that, we can see that sulfur is deficient in its electrons, so we're going to suspect a double bond. So we will move those 2 electrons into the bond. And now everybody has octets, and let's check the formal charges. So we'll start with the sulfur. So remember, we have the valence electrons minus the unshared minus the shared divided by 2. So that gives us 6 divided by 2. So we end up with 6 minus 2 minus 6 divided by 2, which is 3. So that's going to give us a +1 charge on this sulfur. Let's check this oxygen. We've got 6. We have minus 4 minus 2 divided by 2, which gives us a 1. And so that's going to give us a, oops, sorry guys, sorry I lost that part. So we'll do the oxygen. We've got, we started here, 6 minus 4 unshared pair. We have the 4 in that double bond divided by 2. So that gives us 6 minus 4, which is 2, minus 2 gives us a formal charge of 0 on that oxygen. Now let's check the oxygen on the left. We have 6 minus 6 unshared pair minus 2 divided by 2. So 6 minus 6 gives us 0 minus 1, and there's our -1 charge. Okay, so let's see if we can get rid of those charges altogether by rearranging the electrons on that oxygen on the left. So let's try it again. And I'm going to bring 2 more electrons into the bond. So remember, sulfur can form an expanded octet, so we're not going to worry that we've gone over the 8 valence electrons. So let's do this. Let's move these 2 electrons into the bond and recalculate those formal charges. So we'll try the sulfur again. 6 minus its 2 unshared minus the 2, 4, 6, 8 divided by 2. So that gives us 6 minus 6, which gives us the formal charge 0. We only need to do one oxygen because they're identical on both sides. So again, that's 6 minus the 4 unshared pair minus the 2, 4 divided by 2, which gives us 6 minus 6, which is another 0. So each one of those is 0. So you can see that this configuration is more stable because we have 0 formal charges across all of those atoms. As far as resonance, there is no resonance because it's identical left to right no matter how you write it. So remember, for determining polarity by looking at the structure, we're looking for lines of symmetry. So in our first structure, when we had our nitrogen tribromide, we do have one line of symmetry. So if you have one or fewer lines of symmetry, you're polar. If you have more than one line of symmetry, then you're nonpolar. But the only line of symmetry we have on that structure is straight down the middle. So we would have to call this one polar. So anything else like methane would have more than one line of symmetry. So we could divide it in multiple ways and have identical sides or identical halves, and so that would cause that to be nonpolar.